Thank you very much for coming here. My name is Fernando, and I'm going to talk a little bit about an interesting workflow that we have developed to simplify the development of software-defined vehicles and the connectivity aspects of them with AutoSAR and DDS. I'll cover the following topics in the presentation. I'll start with a brief introduction to the evolution in vehicle architectures that we're seeing right now. Then I'll introduce you to DDS for real-time communications. Then I'll talk about the current integration of DDS in AutoSAR, both in AutoSAR Adaptive and Classic, and what are some of the limitations that we have found so far. And then I'll talk about this workflow that I introduced before. All right, so we see that today cars are becoming essentially data centers on wheels, and that is fundamentally introducing a lot of complexity because we need to deal with a really complex distributed system. And because of that, we are seeing now also a shift from traditional signal communication, signal-oriented communication, to more service-oriented communication to facilitate the integration of new information, such as the information that is produced by ADAS systems. We've got now LiDAR and video feeds that are essentially requiring a lot of bandwidth, and that is bringing also the need for introducing Ethernet networks in vehicles, and also finding new higher-level solutions that can simplify the connectivity problem. And that's where we see that DDS is a really good fit for these kinds of systems. So now I'm going to cover a little bit DDS and what DDS is and what it can provide you in the development of software-defined vehicles. So DDS is essentially a collection of open standards that are published by the Object Management Group. This organization is also responsible for other technologies that are pretty well known, such as UML, SysML, and Corba. DDS is, as an open standard, there's multiple implementations of DDS. Right now, we have identified more than 12 implementations, both open source and commercial solutions. DDS is actually composed not only of one spec, but 15 specifications. We are heavily involved, we at RTI are heavily involved in these specifications. We chair most of the revision task forces, and we have authored most of these specifications. And our implementation of DDS has been deployed in thousands of systems, ranging from power plants to vehicles on the road to launch control systems. So it's a technology that is not only well suited for automotive, but it's also being well tested in other industries. And it's actually being introduced in many standards and open source projects and consortia efforts. And right now we're talking about AutoSAR, but it's also part of ROS2, and it's also part of other standards that are basically targeting other industries. In that case, for example, FACE is a standards organization that deals with the A&D market. And in this slide, I wanted to show you a little bit what DDS does and what components it provides you when developing connected systems. So DDS at its core it defines a data-centric publish-subscribe model. So the communication there is basically that applications are going to publish certain topics, and some other applications are going to subscribe to certain topics. They share data. They don't connect to one another. They just simply share the data and exchange data amongst themselves. And what we offer users are standard APIs, so the interfaces are standardized, and we have standard interfaces for many languages. We've got interfaces for C++, Java, C, C#, and we also have other APIs like Rust APIs, Python APIs, and so on. These are the ones that we have standardized so far. And underneath all that, we've got a standard wire protocol that ensures also, besides this interoperability that I said at the interface level, it also ensures interoperability on the wire, so that you can interface on applications that are linked against DDS implementations that are different, can communicate with one another. That's all possible because of RTPS, the real-time publish-subscribe protocol. This protocol actually works usually on top of the transport layer. It can work over UDP, TCP, and so on, but it's built in a way that is independent of the underlying transport layer. So when you, for example, want to communicate with applications that are running in the same host, the same ECU, you can use shared memory to communicate with them, because it's also possible. When you want to communicate with applications that are in the same LAN, maybe you want to use UDP with multicast. And when you want to traverse a WAN, maybe you want to use TCP in that case, right? So that's all possible because RTPS brings in all those features in a transport-independent manner. Now, most recently, we have also added the ability to run RTPS directly over different frames. That's to enable support for TSN. And around all this, you've got another set of standards that complement these basic specifications to provide more functionality. For example, we've got a built-in security model that is, again, independent of the underlying transport. You can have authentication, access control, data encryption, and so on, independently of the underlying transport layer that you're using. So you can secure your data, for example, and send data over unsecure transports. You don't need to use DTLS or TLS or anything like that. You can simply sign your data, encrypt your data, and send that directly over the wire because it's all handled above the transport layer. And that, for example, enables you to send secure data, for example, when you're using UDP with multicast. Now, the actual definition of the data is done according to an extensible type system, which is defined in this X-type specification. That enables you to define your data, to model your data in a way that is going to be future-proof. So you can actually have your initial types defined, your initial data model defined, and then you can evolve it over time while maintaining backward compatibility with existing systems that you've got running. In this spec, you also have the serialization and deserialization rules and the format that you use on the wire protocol. And we said that DDS at its core was a PAP subsystem. We also provide support for remote procedure calls and to request reply kind of patterns. That's all done in the DDS RPC specification. And you can model all of these in different formats. We provide two specifications, DDS XML and DDS JSON, to model your system. And we also have support for the interface definition language to model your types. And lastly, we've got REST APIs and WebSockets APIs to DDS, which are defined in DDS Web, and standard gateways to other protocols, such as like this DDS OPC UA gateway. And now that we have seen the collection of standards that we've got, you can see in a nutshell what DDS does. In this example, we've got 3 applications, a sensor actuator unit, a health monitor, and device control. They are all using DDS, and they are all deployed on different platforms. That means that each of them can be used using a different API. Maybe one application is using a C API, maybe another application is using a C# API. You know, it doesn't really matter. One of them can be running on Linux, and some other application can be running on an embedded platform. But the key here is that they are all using the same middleware, and the middleware ensures that there's like interoperability on the wire. So effectively, you're building some sort of data bus that is going to interconnect all of these applications, regardless of your operating system and other platform-specific features. Now, the way this works is that when you are interacting in DDS, you're actually dealing with your own local cache. You're writing data locally. You are not aware of who's on the other end. Like the applications are decoupled in time and in space. You can be writing your own data locally, and then the middleware automatically is going to handle that the applications that are sending data discover the applications that are receiving that data. And when you call write, you don't know who's on the other end. You just call write, update your local cache, and then automatically the middleware handles that write request that you perform on your local cache gets forwarded to the local caches of the other applications that are interested in your topic. In this case, the yellow topic would be written by this application, and then it will be propagated to the health monitor and the device control. Some of these topics can be secured, so you could actually, for example, have like this data that device control is sending to the sensor actuator unit that can be encrypted or can be signed, and there must be some special access control rules that are enforced there. And the system can be dynamic, so you can add more topics in the mix at runtime, and you can also add new applications at runtime whenever you see that is necessary. And actually, the data that you wrote can be persisted in memory or in disk, so that whenever a late joining application arrives, you can configure your quality of service policies to actually ensure that the information that you already published can be propagated to applications that will join later. And here's a summary of what I explained. You usually define your data using either XML or the interface definition language or JSON. You describe your data, the data that you're exposing or the data that you're consuming. DDS is understanding that data, and it propagates it to all the applications. So basically, when you write, you're doing some sort of data-centric access. You express your intent to write information. You put the information there. And then automatically, DDS propagates the information that you published. Now, that information can be, the way that information flows from producers to consumers can be fine-tuned using quality of service settings. So for example, I might want to send the data for the yellow topic reliably, and the data for the purple topic in best effort. So only the data that is reliable will be acknowledged, and so on and so forth. And DDS will handle that, that the information arrives there, that is acknowledged, and so on. And the information is exchanged in a fully peer-to-peer manner. Each application, the middleware is gonna be making sure that the information that you publish gets propagated to all the applications that are interested in that data, and it's going to send it peer-to-peer. You don't need to actually communicate that data through any kind of broker or server in the middle. And lastly, you can actually optimize the network usage by having filtering capabilities, because DDS provides you with filtering capabilities. You can have content filter, where basically you express which are the kinds of data you're interested in, maybe the subset of the information that you can get from a topic. And or you can have a time-based filter, so that you actually express that you don't want to get data faster than a certain rate. You can express all that, and then the middleware can handle that. For example, on the sending side, you don't get sent the information that you're not interested in, saving a lot of bandwidth. And actually, that's releasing you from the responsibility from your application point of view to actually filter out the data that you're not interested in. For you, once you express that you are not interested in that kind of data, whenever you call read on your receiving end, you're not going to see that data because it's going to be dropped from your local cache. These are like, I talked about quality of service settings before. These are some of the quality of service settings that we support. We describe like the use of reliability. You can have reliable communication and best effort. It's independent, again, of the underlying transport protocol. You can have reliability on top of UDP. And you can also have, I also describe the concept of historical data access. You can store information on your local cache that becomes available to applications that join later. You also have the ability to do content filtering, time-based filtering. And we've got even like QoSs that deal with like aspects that you need to take into account when you're communicating with applications on the other end. For example, you can have a promise of providing updates within a certain time boundary. If you're not receiving those, you will be communicated that the data is not arriving. That's the deadline QoS. You can also detect whether applications on the other end cease to exist. That's done through the liveliness QoS. You can have redundant sources of information that are publishing the same data, and you can pick and choose which one you want to get the information from using this ownership and ownership strength QoSs, and so on and so forth. We've got flow controllers to actually publish the information so that you don't saturate the network. So we've got multiple ways to handle the network efficiently and to determine how the information flows from senders to the receivers, and to actually specify what are the resource limits that your applications are going to have. And all of these can be actually organized into QoS profiles that maybe your organization can standardize and then pass on to the actual implementers who just refer to these QoS profiles by use case or name. And when we spoke before about using different platforms, different operating systems, different compilers, what I meant to say is that you're using different APIs, but the middleware underneath is the same. And that makes it possible to actually have information that can flow from the edge to the cloud using the same connectivity technology. And you can have, for example, in this case, like Leaf ECUs that are here, which might be using native DDS or AutoSAR or whatever, and that information can actually be that can flow from the edge to the cloud using DDS underneath. You don't need to have like gateways or translation units all over the place to actually make sure that the information is propagated. And also, you have the ability, because there are safety certifiable versions of DDS, such as Connect Cert, you have the ability to have the same middleware handle safety critical data and non-safety critical data, and that can all use the same software to connectivity technology again. We can save you a lot of cost. Again, reiterating, you've got multiple ways to access the same middleware. You can use native DDS, obviously, with different APIs for your programming languages. You can use ROS 2, and again, send data, but you're, again, accessing DDS through the ROS 2 APIs. And with AutoSAR, you've got AutoSAR Classic and AutoSAR Adaptive, both support DDS. So you can have AutoSAR Adaptive applications, AutoSAR Classic applications, ROS 2 applications, and native DDS applications talk to one another because they're using underneath the same middleware. Now, let's talk a little bit about the status of the integration of DDS with AutoSAR. We started working on the integration of DDS with adaptive AutoSAR back in 2017, 2018. The first version of the that introduced support for DDS was version 1803, and that's when we published the network binding for Aracom, the DDS network binding for Aracom. And that's been out there for a while. I think I introduced that at the AutoSAR Open Conference back in 2018. That was also held in Shanghai. Now in 2022, we released the first version of AutoSAR Classic that introduced support for DDS. In this case, was signal-based communication where we supported. And now, most recently, last year, we introduced support for service-oriented architectures with AutoSAR Classic as well. So we moved all the parts that were explaining how to implement SOA with DDS to the foundation. And then that part is basically shared from both AutoSAR Classic and AutoSAR Adaptive. And then in Classic, we introduced the concept of the DDS transformer. So right now, you can actually do with DDS all of the things that you could do using AutoSAR, but so you can do service-oriented architectures with DDS in AutoSAR, but some of these aspects, as we'll see later, and the use of the AutoSAR APIs sometimes provide you with some limitations, because you're not just using the APIs of DDS directly. And that specifically relates to the concept of data centricity that we have introduced before. Now, in this case, we have a simple example with an AOC control system, which is divided in different zones. Now, in this case, if you wanted to implement it using service-oriented architectures, you might define different services that are available in the different zones. You can actually control these services from different locations, so you're going to have different sources for calling the methods that these services offer. So you will, for example, instantiate, in this case, 8 service instances. You will have different sources that can call those service instances. So obviously, these sources would have to bind to the service instance that you've got on the other end, and then they will call the methods as they see fit. So that implies having a lot of proxies that can connect to a lot of services, and that can drive the complexity up as a system and needs to scale. If you think about the data-centric concepts, in DDS you could basically simplify this thing, having a single topic that is going to be the AC control request. That topic can encapsulate all the information that is common to all the service instances. So for example, you can have a service ID that identifies the specific instance that you're targeting. You could encapsulate the source of the requester in this case. You could encapsulate it in here into some sort of field, and then you can encapsulate the command. So effectively, all the senders can have a single data writer, and all the receivers can have a single data reader, which simplifies discovery a lot. And then all you need to do from the sending side is to write that topic to the appropriate destination, and then the middleware automatically is going to handle without you having to actually connect to the receiver. It's going to handle that data arrives on the receiving end, and that reduces a lot of the traffic and also the complexity in the client side. Here's like what it would look like in the end. You will have the vehicle sonar controllers, which would propagate the information to the actual ECUs, and then you would write from different parts of your system using the same control topic. It will all be handled by the middleware, how these applications discover to one another, and how the information flows from the senders to the receivers. And you can actually fine-tune the way that information flows by choosing the right QoS policies. So for example, in this case, you will configure these commands to be reliable, because you want that information to be actually acknowledged. You want it to arrive on the other end. You would say that the history, maybe you don't have to keep all the history that you've got. Maybe you just want to keep the last sample that you received. And you can have a certain lifespan, and you can even have a content filter, so that you can filter out the requests that were not meant to you. Now that we have covered the part that is specific to DDS and the way that DDS works in AUTOSAR, and the limitations of the SOA when it comes down to using the full potential of DDS, we can take a look a little bit about this workflow that I discussed before. Now we have multiple, I spoke before about DDS and DDS XML and DDS JSON. These are two specifications that provide you with syntax to configure DDS systems. For example, they provide you with syntax to define your DDS types. That is the type that describes the information that is exchanged in DDS. We've got syntax to define QoS libraries and QoS profiles. We've got syntax that you can use to model your DDS system, the domain participants you're going to have, the writers, the readers, and your topics. And then lastly, we've got syntax to define applications, which are a collection of domain participants. Anyway, now, the thing that we added more recently, and that was part initially of our support for DDS and TSN, which is now being going to be part of DDS XML and DDS JSON, is the ability to define nodes, and also to design deployments. Now, the nodes are basically where the applications are going to run. So your deployment is going to map your applications into specific and specify that you want to run those applications to specific nodes. In these deployment configurations, you can also specify configuration parameters that are specific to a domain. In the case of TSN, we provided here some TSN requirements that you've got, like where you had the ability to basically configure certain traffic shaping mechanisms using TSN. But we could also standardize AUTOSAR-specific configuration parameters that can be then propagated into AUTOSAR-specific tools, and we'll see that how we do that later. But anyway, the key here is that we've got syntax to define DDS systems, define your DDS applications independently of where they're going to run and in which platform they're going to run, and we've got the ability to define deployments, right, using XML or JSON syntax. And here's an example of this syntax. Here, for simplicity, we created two files, a system design document and a system deployment document. In the system design document, you basically define everything that is independent of the deployment configuration. So you define your types. Here's just like a struct, name hello world. You define your QoS libraries. You define your applications, which basically are using certain domain participants, which are going to publish or subscribe to certain information. So that's all independent of where you're going to run this thing in AUTOSAR, native DDS, whether it's going to run on Android or Linux. Now, you can actually have another file where you specify where this DDS application runs. You can say my application is going to run on node 1 or node 2 or whatever. And I'm actually going to configure some AUTOSAR-specific settings here. Maybe the use of a stack that I'm going to have, like whatever comes to mind, right? Now, what you end up having is like a system design document and a system deployment document that when you put them together, you have all the information that you need to actually deploy your system and generate code for your system and for your applications. Now, we have developed a code generator that can ingest this kind of syntax. This code generator has different generators. In this example, what we've got is that, look, I've got my system design document and my system definition and my system deployment document. I'm going to call my code generator, and I want you to create a native DDS application. So I call my native DDS generator, and I generate the type support code, which is basically the code that is going to indicate how to serialize and deserialize the data. I'm going to write the DDS entity support code, which is basically the code that pre-populates all these entities to me, so that I can just simply, if I want to write, I look up the data writer, and I call write, the write function. If I'm going to read, I look up the data reader, and I call the read function. And with this, I can basically deploy my system using DDS native APIs, and I'm good to go. Or I could call the AutoSAR complex device driver generator, maybe, which is going to generate me a DDS CDD, and it's going to generate a bunch of RXML files that I can actually load into existing AutoSAR tools. And then I also generate the same kind of code because I need DDS specific code to interface with the DDS part. Now, what in the end happens is that now I have RXML files that I can import into the AutoSAR tools. In this case, we are using Vector's DaVinci Developer. We load all the RXML files that I generated. Now if I've got the files loaded, then now I can map these port prototypes from the application side to the DDS CDD. As you'll see here, like if you look at the port prototype types, I can look at actually the types that I define in my DDS XML are now have been propagated through the RXML into the tool, and I'm good to go. Now I can actually, now that I have run my application and done with the application side, then I can actually configure, I can assign the runnables to OS tasks. So I'm going to use, like in this case, Vector's DaVinci configurator. Now I assign the runnables to OS tasks, and I generate basically the software component template and the basic software module, and I'm good to go again to deploy your applications. So basically, from some XML documents that were independent of the way that I was going to deploy the application, that were independent of the API that I'm going to use, I have been able to derive running applications that I can simply run on a certain host. I can create native DDS applications, and I can create AutoSAR applications, right? And all those requirements, all those applications can be simply defined in XML, and all the complexity can be derived to code generators. And that's a really powerful concept. And this concept can basically be extended. In this case, I could derive these DDX XML or DDS system design and system deployment files, maybe from some existing RXML configuration, which running some sort of converter I can create the XML files from, and then I can run the code generator again. And the code generator doesn't only have to create CDDs, it can also create basic software modules. Maybe I want to base that on the specific AutoSAR specifications that are dealing with DDS. So now I can have all kinds of use cases and generators that can basically map my needs. And it's an extensible system. You can add additional steps. It's really flexible. Anyway, so just to wrap up the talk, here's a summary of what we described. Software-defined vehicles are becoming like really complex distributed systems. DDS is providing you with a really comprehensive connectivity solution. It's based on open standards. There's multiple implementations. It's being well proven in highly demanding systems. It provides you with a rich set of quality of service policies that you can use to fine-tune the way that information flows from consumers to receivers, the resource allocation that you have. It's well suited for the application of solar architectures and, in the end, to the definition of software-defined vehicles. It's got a proven integration with AutoSAR. It's also part of other frameworks. And in the case of AutoSAR, it's basically implementing the existing APIs and the existing paradigms that you find out there, for example, service-oriented architectures. And because DDS uses a common wire protocol, then it can also interact with applications that are not using the same API you're using. DDS applications that are native can interface with DDS applications that are using AutoSAR or ROS2. And but it's true that in those cases, sometimes the use of service-oriented architectures or other kinds of models can prevent you from following a data-centric approach that might be simpler to solving your problem. Now, lastly, we introduced this standard configuration model based on DDS XML or on a standard schema files that you can actually use to describe your system and generate applications for various platforms based on a single source of truth. And that's really powerful because it basically, for example, an organization or an OEM can define in a higher level like the DDS concepts, and then it can pass them on to other the actual implementers, which are going to deal with that. They can express the requirements in XML, and then the actual implementers can generate the code for that and create the actual applications, right? And that's all based on standards, and it's compatible with existing tooling. Like the code that you generate can be imported into existing AutoSAR tools, and in leverage is basically what's already out there. It's just providing you with a simplified way to express your requirements and to provide them to the actual implementers. And with that, I'm open to questions. Thank you very much for your attention.
Thank you for your presentation. I'm just curious about the resource consumption regarding the classic AutoSAR integration. Not sure whether there is some mitigation or way to adapt to AutoSAR class platform well if we need to reduce the resource consumption when using DDS.
You mean the resource consumption of the DDS library itself that you're using?
Such as the discovery. So it uses RTPS protocol, right?
Yeah.
And if there are many nodes connected, and the number of nodes maybe can be unknown, and if it exceeds some number, then maybe heap size will be consumed much, right?
Yeah.
So do you have a way to mitigate or AutoSAR level move to to do so? Yeah.
I mean, obviously, like when you're building a system that is really complex, and if you're doing fully peer-to-peer communication, then there's obviously an explosion of the number of applications that you need to talk to, right? So there's two parts here. Like usually in these kinds of environments, maybe you don't have dynamic discovery. You use a static discovery to ensure that all that traffic that would be exchanged to complete discovery is already done. So you already have all the applications you need to communicate pre-established. And then obviously if you're going to have to discover like there's like also the quality of service settings that deal with resource allocation. You can basically set some limits, try to reduce a lot the memory that you're using. But if you end up having a fundamental problem that is like I'm trying to scale to 7 million nodes, and that's impossible given the resource constraint environment that you're using, in that case, sometimes what we have seen is that there's sometimes the need to have a gateway that that basically encapsulate the discovery to certain areas, and that you talk to that gateway, everyone discovers that gateway, and then you bridge the traffic through that. But many times that's not necessary, but sometimes to scale, you need to divide the communication into different zones, and that the traffic is reduced significantly because you can actually address that not all the applications need to discover all of the applications in the world, right? Which is sometimes a problem.
I see. So that means by reducing the discovery, so you can reduce the memory users.
Exactly. If you need to. But again, like when you use a static discovery, sometimes this is not a problem. And yeah, like there's multiple aspects to that question, right? But yeah.
I see. Thank you.
Yeah, you know what it is. All right. So I gave you back 10 minutes of your time. You can go take a nap.